Hello, this is Dr. Kanthi Sudha, and I would be talking about Smith chart basics today, which happens to be one of the topics in electromagnetic waves and transmission lines. So let us see what will be the flow of presentation today. So I'll be talking about VSWR and reflection coefficient and Smith chart basics, as well as plotting and interpreting complex impedances in a Smith chart and the applications of Smith chart. So before going into the Smith chart, I think we have to understand the basic like VSWR, voltage standing wave ratio, and reflection coefficient, because these happen to be the key parameters which will help us in the Smith chart. So why we are talking about voltage standing wave ratio? First of all, what are standing waves? In the context of a transmission line, if you are connecting a source to a load via your transmission line, there is always a tendency that you may have some kind of an impedance mismatch at the load point, because of which there might be reflections coming back from the load towards the source. In such a scenario where there is a combination of the incident and the reflected waves, that is when you tend to get standing waves. So with respect to these standing waves, when we look at, so we talk about the parameters like voltage standing wave ratio. Now voltage standing wave ratio is nothing but the voltage ratio of the signal on the transmission line. So it is the ratio of the maximum signal, that is Vmax, to the ratio of the minimum signal. So Vmax is considered to be the maximum voltage of the signal along the line, and V minimum is considered to be the minimum voltage along the line. So since the comparison is between two voltages, VSWR definitely will not have any units. It's a ratio, and it is generally compared to 1, because when V minimum is going to be equal to V maximum, VSWR is going to be 1, and similarly when V minimum is going to be equal to 0, VSWR can be infinity. So the values that your VSWR can have are between 1 to infinity. Now coming to the reflection coefficient. What is reflection coefficient? So reflection coefficient is basically giving us the fraction of the incident signal that is being reflected from a mismatch. Now this fraction of a signal that is being reflected back can be expressed in terms of the power ratio, that is the signal of the reflected wave or the power of the signal reflected wave to the power that is considered to be in the forward traveling wave. Sometimes it is also expressed in terms of percentage also. So the reflection coefficient is always expressed either in terms of a variable called rho, which is notated as per the given slide, and it is directly linked or related to VSWR by the expression rho equal to VSWR minus 1 by VSWR plus 1. Now what is the relation between VSWR and reflection coefficient? Now VSWR or reflection coefficient, both are interlinked. So that means if you know one of the parameter, you can automatically calculate the other parameter. So previously we have seen how rho is related to VSWR. Similarly, in the similar fashion, we can also talk about VSWR being equal to 1 plus rho by 1 minus rho. Now reflection coefficient, when you talk from the perspective of the load, it can always be given as ZL minus Z0 by ZL plus Z0, where ZL is considered to be the load impedance and Z0 is considered to be the characteristic impedance of the transmission line. Or in a generic way, if you want to write it, you can also write it as rho equal to Z minus Z0 by Z plus Z0, where Z happens to be your reference impedance. So whether you are calculating the reflection coefficient with respect to the source, or whether you are calculating the reflection coefficient with respect to the load. So this can be clear by taking what kind of a Z you are using at this point. And Z, when you say, we always consider Z to be a complex impedance which consists of a real term and an imaginary term, like Z is equal to R plus JX, where R is considered to be the resistance and X is considered to be the reactance part. So now let us delve into the Smith chart basics. So it is a known fact that a Smith chart has been introduced by Philip Huger Smith, who has introduced this concept, the Smith chart, in the year 1939. So he has published this in an electronics magazine on how a Smith chart can be helpful in the transmission lines as well as in various scenarios. So it is basically considered to be an essential tool in radio frequency engineering and circuit design. And originally it was created to simplify the mathematical calculations and allow the problems to be solved graphically using a compass, ruler and a pencil. and it was very backdated. As you can understand, it is 1939, but still till date we have been using Smith chart in various kinds of applications where it has proven to be a very resourceful tool for us. And today we are learning about the Smith chart in this particular context where we want to understand how a Smith chart can be used at a basic level, especially in the context of the impedance. So its utility is in visualizing complex impedances. So we are going to see that today. And similarly, it is widely used to tune and verify the matching networks. So why we are going for a Smith chart? So if you look at the transformation, that is from a Cartesian to a Smith chart. So if you understand a Cartesian coordinate system, so let us consider a simple Z. We were talking about a complex impedance where we were talking about R plus JX. So if I want to represent R plus JX, so how do I represent? I represent it either in terms of what you call in the axis that is visible here in the slide, where I am talking that the real part of the Z, that is R, is along the R axis and X, the reactance, is along the vertical axis. Now if I have to notate a particular point, let us say R plus Jx, it is going to be above the R axis in the right side quadrant. And similarly, if I am talking about R minus Jx, where I am talking about a negative reactance component, that is going to be below the R axis. So this is what we can understand from the simple Cartesian representation of a complex impedance like R plus Jx or R minus Jx. Now, how we are bringing that into a transformation, or how we are changing that into a Smith chart. Now, Smith chart is also going to be same thing. Whatever we are trying to represent in Cartesian, we have just used the same concept where in a chart of a circular fashion, which we can see over here. So basically we are trying to use the upper half. Whatever is this upper half, this is basically representing the positive or what you call Jx, and similarly the bottom portion, that is the red colored one, that is indicating the minus Jx term, or you can say the upper portion is an indication of an inductive and the lower portion is an indicative of a capacitive. Since this axis, the horizontal axis, is going to be your resistance or your R, so above axis is inductance and below the axis is your capacitive. And the imaginary and the real part of reflection coefficient, if you look at, or the real part of reflection coefficient is going to be in this portion of the graph, and the imaginary part of the reflection coefficient is going to be on the upper portion of the graph. So as simple as it. So whatever I have told you, so this Z, if I am indicating, this is R plus Jx, and similarly this is your inductance and this is your capacitance, which is being transformed from Cartesian to Smith chart. When you convert it, the upper portion is basically your plus X, and your lower portion is the indication of your minus X, or it's an inductive or a capacitive, and the line separating these two areas or these two portions happens to be your resistive. So this is how a Smith chart looks like, and if you look at the first go, you can see there are a lot of circles, lot of lines, lot of values being indicated on this particular Smith chart. So Smith chart is considered to be used for several various applications. Almost they have identified close to 200 applications which can be done using the Smith chart. But we are not delving into each and everything. We are just looking at the basic part to understand how a Smith chart can be simply used to represent a complex impedance, or how we can identify or read from a Smith chart if you are given a particular value. Okay. So let us first consider the prime center of your Smith chart. So if you look at the prime center of the Smith chart, so the prime center means the center line, the line, or if you look at the previous Smith chart, I think you can understand we are talking about this line which is at the center of the Smith chart. Now this same line is basically we are talking about where we want to understand what is the basic prime center of the Smith chart. So it is considered that the center of the chart is basically related to your impedance Z0, which is equivalent to which is 50 ohms in most of the RF systems. So if you see this red colored point, whatever is there, is basically indication, or here the value is showing 1. So 1 is basically the normalized impedance. Normalization means you are dividing the impedance Z by 50 ohms, because here our reference is 50 ohms. So we are normalizing that value to equal to 1. So 50 ohms by 50 ohms, that is what is your value normalized to 1. So this 1 is indicating 50 ohms. Now in the same line, if you proceed to go to the other side, for example here in this case, there is a 2, the value is 2 here. So in this 2, if you take, how do you normalize it? I mean, how do you identify the impedance corresponding to the, or the resistance corresponding to it? So since we said it's normalization, so the normalized value is 2. So which means to say that we have to multiply 2 with 50, so which makes it a value of 100 ohms. Now similarly, if I proceed to the left hand side, so for example here there is a value called value you can see, which is 0.4. Now 0.4 is the normalized value. Now this normalized value, when you multiply it with 50 ohms, that is when you are going to get 20 ohms. So basically this total line is basically an indication of the various points corresponding to the values that are indicated here. So like that, any point you take, you just, all you have to do is take the normalized value, whatever is indicated on this, and multiply it 50 ohms. That is when you get the exact value of your resistance or your impedance. So all values on the Smith chart, if you take, these are all normalized by the same value. That means correspondingly each and every point has been normalized to a particular value, say in this case 50 ohms. Now the same thing, sometimes in some of the references we also take 75 ohms also to be our referral. So in such a scenario, we will have to normalize it with respect to 75 ohms. So whatever normalization you are doing with respect to any particular value, you will have to follow it throughout the chart for each and every value. Okay, so this can be used for any kind of a system impedance. So let us see the resistance axis. So this is the center line which we are talking about. So previously we have seen this is the 1 point. Now as we go towards this end, that is left end, you can see that it is corresponding to one extreme value, and if you go from 1 to towards right side, it is corresponding to another extreme value. So if you go to the right side, this extreme value on the resistance axis is basically corresponding to your open circuit, which is corresponding to infinity ohms, or you can say VSWR is equal to infinity. Now the same thing, if I am extending from towards my left side to the left hand extreme, so this is going to correspond to 0 ohm, which indicates a short circuit, and or it is corresponding to VSWR equal to infinity. Now let us look at the resistance circles. So there are a lot of circles which are marked here. Now for example, whatever center line I was talking about with respect to the resistance axis, any particular value you take, okay, so the circle that is passing through that particular point tangentially, so that is called as your resistance for circle. So for example, so here you can see R equal to 1. So here we have taken R equal to 1 on this resistance axis, and there is a circle which is passing through it, making a tangential with respect to that particular value. So which means this is R equal to 1 circle. Now same thing, this is R equal to 4 circle. The green colored one is R equal to 4 circle, and the red colored one is your R equal to 0.6 or R equal to 0.2. So anything, any kind of a circle which is intersecting your resistance axis at any particular point, so it is going to be a resistance circle of that particular value. So R equal to 0.6, R equal to 1, R equal to 1.4, R equal to 4. So like this, any value on the Smith chart you take, you can correspondingly find a circle which is going to be in tangential with it, and based on that you can arrive at the value of what is the resistance or the R value. Now similar to resistance, we also have reactance values. Now reactance circles are something which are like this. So each reactance circle is again starting from the resistance axis, and it is all the way going to the end of the chart, towards the end of the chart. Now these are two lines which are showing the curves, reactance curves, which are ending at two different points. For example, this is ending at a point of 1 and this is ending at a point of 3. Okay, so these are basically reactance circles. Reactance means you understand that it is X value. So we are talking about a normalized X value corresponding to 1, normalized X value corresponding to 3, which indicates that X values are also normalized values, just like your resistances which we were talking earlier. So these values also are normalized to a impedance. Let us say in this case it is 50 ohms. Okay, so these are the reactance circles. So the most important points on a Smith chart are that one extreme end of the resistance axis is your open circuit, the other extreme end is your short circuit, and the center point on your Smith chart is your matched load, which is corresponding to your rho equal to 0, or reflection coefficient is equal to 0. So matched load indicates that you are talking about a load where there is no reflection coming back from the load, because match load itself indicates that whatever your source impedance is generating, it is being absorbed by your load, which indicates that it's a match load. The reason why it's called a match load is that all the signal that is coming from your source is getting absorbed by your match load, and that's the reason why your reflection coefficient is equal to 0. And similarly, if you talk about your open circuit, your rho is equal to 1, and if you're talking about a short circuit, rho equal to -1. Okay, so like this we have all the points marked on the Smith chart. Now let us see or go ahead with interpreting the complex impedance. Now, because in a Smith chart we want to see how a complex impedance can be represented using Smith chart. So that is what is of our interest now. So let us see how we can represent this. Now let us see this particular value 100 plus J 75 ohms. So how did we get this 100 plus J 75 ohms? Now there is a point. Now for example, you can see here there is a circle which is passing through a normalized value of 2 here. Okay, normalized value of 2 on the resistance axis, which means the corresponding resistance value is 2 into 50 ohms, which means your R value is going to be 100 ohms. Okay, similarly, when you talk about the reactance curve, now the reactance curve is here somewhere. So where you can see the value corresponding to that, and that value, that corresponding value, whatever we have on the reactance curve into 50, that is going to give you your 75 ohms. So that's how you have arriving at a complex impedance. So the intersection of your resistance circle and the reactance curve, wherever it is there, that is going to be your impedance corresponding to 100 plus J75 ohms, because this red circle is going to be your R equal to 100, okay, because it's passing through the normalized value of 2, and this reactance curve, whatever is there, is corresponding to the reactance value of 75. So that's why the intersection of this reactance curve with the resistance circle, that is where you can identify your complex impedance, that is 100 plus J75 ohms. Okay, so this is how you can plot your complex impedance. So if I am asked to plot 100 plus J75 ohms on a Smith chart, so how do I do that? I first normalize it. Normalizing means dividing this impedance value 100 plus J75 by 50. So 100 by 50 is basically 2. So you have to draw a circle, you have to take the resistance circle which is passing through the value of 2, and similarly 75 by 50. Okay, 75 by 50 is 1.5. So 1.5 is the reactance value where I have to take my curve. So the reactance curve has to be taken from 1.5 value and all the way running through the resistance axis where it is the origin point. So the curve, wherever it is intersecting the resistance circle at 2, that is where your 100 plus J75 ohms is going to be there. So this is how easy we can plot the complex impedance in a Smith chart. And similarly, when we talk about normalization, so generally we give the normalized value also. So for example, in this case, the normalized value is given 0.3 minus J 0.4. Now, depending on your impedance, what impedance you are using for the normalization, you can always multiply it with the normalized impedance and get the exact load impedance value. So that is how you can read from the Smith chart using your normalized impedance values. So this is how the basic Smith chart looks like, and as I told you, Smith chart can be used for various applications apart from this knowing just the complex impedance or reading the complex impedance. They're also used for, most of the time they're used for impedance matching. So how can we provide impedance matching, or if you want to find the impedance, some unknown impedance, that also can be done. So there are various applications for which a Smith chart can be used. So we will be discussing about the applications part of the Smith chart now. So Smith chart, as I told you, it can be used for impedance matching. So you can find the proper impedance value which is required, as we are talking about, so that the line is properly matched or properly terminated. So it can be used for transmission line analysis. Like for example, you want to find out what are the values corresponding to this reflection or reactance or resistance, all these parameters or transmission line parameters. So all this can be found out using your Smith chart. Similarly, we can find VSWR and reflection coefficient value from determination also can be done from the Smith chart. And also we can see the frequency response representation, that is how your load impedance is varying with respect to frequency. So generally there will be a trace kind of a curve which takes place in a Smith chart, based on which we can always see how good it is matched to the load, because we were talking about the prime center, which I told you, where we said that ZL ZL is corresponding to your normalized value of Z0, which is equal to 1. So whenever your trace is passing through that particular value, that is when you can say it's a resonant frequency corresponding to the circuit. So frequency response representation is also a very important application, where we can get to know how the load impedance is varying with respect to frequency. And similarly, we also use the Smith chart for antenna design and tuning also, which is probably a bit higher level compared to the course whatever I am talking about. And similarly, the parameter visualization. So whatever parameters you want to look at from the Smith chart, so all these parameters you can visualize them without doing mathematical calculations. It's so it was so easy with the Smith chart, just because all it required was, you require a pencil, you require a compass, you require a scale. So that was it, and there are a lot of values which were interpreted from the Smith chart, and this has really opened a wide window for a lot of applications related to RF engineering. So hope you like this, and any queries you can drop in your comments. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.